All right, so today's webinar is about using Coreform Cubit as a powerful front end for third-party CAE solvers. And we're sharing a case study with how CAE Fidesis has been using Coreform Cubit for several years as a front end. So as a reminder, at Coreform, our goal as a company is to enable better simulation through better geometry. And the origins of our company is in commercializing a new technology called isogeometric analysis. And we have now an IGA solver called Coreform IGA. We also distribute and develop the Coreform Cubit advanced meshing software, and that will be the focus of the webinar today. The next webinars in our series will be in April and May. We'll be digging more into Cubit in April with a focus on the Coreform Cubit Python API. And then in May, we'll have our next Coreform IGA webinar about predicting the onset of failure with IGA. And those will be hosted by Greg Vernon at Coreform. But today, again, we're excited to have Dr. Anatoly Vershinin, the CTO of Fidesis LLC, with us to share how his company has been using Coreform Cubit as the front end for their CAE solver for nearly the last 10 years. Just some housekeeping. This webinar, of course, will be recorded. As you have questions throughout the webinar, please feel free to ask us questions in the Q&A. We have Carl Merkley, the software architect here at Coreform, and myself will be answering those either in the back channel, or we can pause the presentation to answer those as needs be. And the agenda then will be introducing a little bit of Coreform Cubit and its API. Then Anatoly will introduce his company CAE Fidesis and how they've been using Coreform Cubit, give a live demo of their software, and then we'll have time for Q&A. So the value that we hope you'll get out of attending the webinar today, if you are a solver developer, then you should learn how to accelerate your time to market with your solver and improve your user workflow through using a customized Coreform Cubit integration, like how Fidesis is done. And if you're an analyst, then this is the chance for you to see how CAE Fidesis, you can use their powerful simulation software built on Coreform Cubit to improve your simulations. So if you're not familiar with Coreform Cubit, we've been developing this software over the last 20 years or so with Sandia National Laboratories. It's a comprehensive industry-leading hex and TET meshing toolkit. It's relied on by leading industry and government simulation groups for some of the most demanding simulations. A few months ago, we launched a free non-commercial license. So if you are in academia or otherwise just learning, then that's become a popular option to get into Cubit. But today what we will be focused on is using Cubit for advanced scripting, automation, and the API. So the Coreform Cubit interface API that we'll be talking about today is included in no cost with every license of Coreform Cubit. Some of the benefits of this is it leverages the ability of Cubit to replay your journal files, leverages the power of Python scripting, ability to customize the GUI, and then integrate this with your application either through Python or C++. And we can get more into the details of the architecture and the Q&A, but there's extensive documentation about this at coreform.com. It's quite robust. It's been in development for over a decade. And you can just import the entire Cubit core executable into Python as well. So with that introduction, let me turn the time over to Anatoly, and he will introduce more about CAE Fidesis and how they are using Coreform Cubit API with their software.
Thank you very much, Matt, for the introduction and for giving this opportunity to share our experience about our integration with Coreform Cubit and how we're using it in our software Fidesis. Hello, everybody, and thank you for attending. My name is Anatoly Vershinin. I'm a CTO of Fidesis and also associate professor of Lomonosov Moscow State University, where in 2009, based on the research group as a classical university spin-off startup, Fidesis was created. And starting this time, we are developing the next generation computer-aided engineering software for strength engineering analysis. Fidesis is already used now in mechanical engineering, mining, oil and gas, different industries. If we have enough time, I will show you several examples in the end. Also, I should say that Fidesis has several offices right now all over the world, including the headquarters in Moscow, but also we have a sales marketing office in New Jersey, USA. We are the member of NAFEMS, which is International Association of Engineering Simulation Modeling, and also the partner of leading international vendors. For example, you can find us in the marketplace of Microsoft and Amazon. Our team, most of them are from our alma mater, from Moscow State University. Currently, it's about 35 programmers, developers, the core of the team. But also we work closely with several universities, Institution of Russian Academy of Sciences, and also research universities from the United States. And our board of directors consists of the former VPs of leading engineering software vendors. Speaking about our history of our collaboration and integration with Cubit, everything started in 2010 when we were in active search of the proper solution for our preprocessor. And at this time we tried, you see the letter from Sandia National Lab, for the first time we tried to use Cubit as a potential solution for the preprocessing, for mesh generation, geometry processing, etc. And being satisfied, absolutely satisfied with this solution, in 2012, Systemsoft, the predecessor somehow of Coreform and Fidesis, signed an OEM agreement, and this is a confirmation of this agreement, where our companies agreed on licensing Cubit as an OEM solution for Fidesis preprocessor. In 2013, we organized a personal meeting at the COFES, Arizona, which is a leading engineering conference happening each year in Arizona. And later on, the representative of Systemsoft visited also our office in Moscow. And this photo is actually from our meeting with the Systemsoft guys from Polkaro here, Randy, our meeting in 2013 in Arizona. And actually there was a fourth person making photos, 3 of us. And I don't know, could you guess who is it or not? But the fourth person was actually Ted Blaker, the father of Cubit. And it was a big honor, and I'm really proud to meet Ted Blaker personally. So it was really Fab 4, our meeting there at the COFES. As I said, we have chosen Cubit as a preprocessor for the Fidesis, and Fidesis consists of 3 major modules: preprocessor, postprocessor, and the solver calculation, which performs calculation in the Fidesis kernels. Both preprocessor and postprocessor has GUI, and also thanks to the Cubit API, it has quite functional and quite useful programming interface, console interface based on Python. So the end user has always an option to write scripts to make automatization of several operations, and I will show examples later. In terms of functionality, Fidesis consists of the several modules and 2 major products, the two major versions. The basic version, Fidesis standard, for the linear static dynamic model buckling analysis problems, everything in linear formulation. And also Fidesis Professional for the nonlinear problem, different kind of nonlinearities, like for example, contact problems, hyperelastic materials, which is physical nonlinearity, and geometrical nonlinearity, and of course all of possible combinations of these kind of nonlinear things. And both standard and professional may be extended by additional modules, which is HPC for high performance computing and parallelization, dynamics for solving non-stationary wave propagation problems, for example. And here, one of the distinctive features of our software, spectral length method, is used. And also fidesis composite, which is last but not least, and it is dedicated for solving problems for the analysis of composite materials with, let's say, complicated heterogeneous microstructure. Thanks to Cubit, which we are using as a preprocessor, we also support different CAD formats for importing models into the preprocessor, because as it's clear, CAE software is very actively and very frequently using CAD data format as an input. And once again, thanks to Cubit Translator, we do support not only general purpose formats like ACE, IGSTEP, but also commercial formats from different commercial vendors listed on the slide. And of course, this gives much better accuracy and less risk when importing complicated CAD model into fidesis preprocessor. Speaking about the list of formats, you could see them on the left-hand side. And what I should draw your attention that there is not only CAD format, but also Cubit does support importing also mesh formats from either additional other CAE software or mesh generation software, or in general purpose formats like IDEAS or STL. And several others. So there is again always an option to import either this CAD model or mesh model. And on the right hand side of my slide, you could see all of the different types of finite elements which Cubit mesh generator could produce, like beam elements, shell elements, solid elements. All of these elements, this element zoo somehow is completely supported by fidesis solver. So curvilinear elements, first order, second order, hybrid meshes consisting of different type of geometrical elements like tetrahedral, wedges, pyramids. So the user is completely free and flexible to make discretization consisting of any possible combination of all these elements. However, one element is still missing, and maybe Coreform developers should take it into account if we speak about not only finite element mesh, but also finite elephant mesh. So hopefully in the next release of Cubit, this will be available as well. Speaking about integration and importing external formats from external software into fidesis, there is an example how the end user could just one single click button and import the model from Autodesk Inventor into fidesis without any manual work, without any specific operations. It's just, again, one click button and everything is done automatically. And this was possible by developing the special plugin for Autodesk Inventor using Cubit Python API, which was mentioned by Matt. The similar example is presented here for the integration with BricsCAD, another example of CAD software. But this example is a little bit more extended because here we're not only importing the model, but the designer, the user of BricsCAD, also performed the fast structural analysis at the early design stage in order to make sure that the design prepared in BricsCAD is robust and solid enough to, let's say, continue with manufacturing of this design. And I will speed up the process. However, all the videos are available on our YouTube channel for those who is interested in detail. So look at again after the webinar. So here you could see actually the overview of the GUI of the preprocessor of fidesis based on Cubit. And all the operations which the user is doing here, like mesh generation, setting boundary conditions, material properties, is duplicated accordingly by the so-called scripting command in the command line. Why I'm showing this? Because the user designer will use this command later on for the automatization of the analysis process. But for the first time, everything is done manually by clicking corresponding buttons and elements of GUI in order to specify fully the FEA model with the boundary conditions, mesh, material properties, etc. And then we click button start calculation. We see that the analysis is done, and we open result and see what are the actual result in post-processor, fidesis viewer. And let's say we see that our displacement, which is actually 17 millimeters, turned out to be too much. So it's not allowable for such a design. We need to reduce them drastically to be compliant, let's say, with the strength standard. So before going back to the BricsCAD, first thing we do is we save the journal file, which Matt mentioned in his introduction. And the journal file exactly consists of all the history of the comments which was generated by clicking buttons in the GUI. This is very useful, and we need these journal files later on in order not to click again all the process. After we save the journal files, we go back to the BricsCAD and we modify our design. So what we do actually, we add such kind of edge, which we hope will make our design more robust for the bending force, so it will be more rigid. But we never trust ourselves as completely being compliant with the simulation-driven design ideology. We again click button and export our model into the fidesis preprocessor using the plugin we developed, and we see the modified design in the preprocessor. And next we open the journal file. So we are not going to, once again, to assign material properties, generate mesh. We just open the new, we open the saved journal files, and then click the button play. Yeah, you see it here. And all the operations, as you could see, were done automatically. Meshing, material properties, boundary condition, everything done automatically, including the simulation itself. And once the simulation is done, we go to the post-processor and see that this time displacement is 100 times less than it was for the previous design. So such a simple example demonstrates the workflow of the simulation-driven design when the designer optimizes its part by doing repeated simulation and automatic import-export the model from BricsCAD into fidesis. And all of this was possible again using Cubit Python API.
Anatoly, that's a really powerful integration. Thanks for sharing that. You might want to move your mic just a little bit away from your mouth. We're getting a little bit of feedback.
Yeah, okay. Now it's better. Okay.
That's perfect. Yeah.
Okay. The next example, continuing the story about integrations, is the using Cubit Python API. Matt, do you know how can I remove this top part, because I think
we can only see your slides, so it looks good on our machine.
No problem. Okay. The integration with the geomechanical software, geophysical software, which was actually announced in the topic of today's webinar, and this is example of integration with Micromine, which is the software for the geological modeling. So in this case, the user of this software is geologist who builds the 3D model of, let's say, reservoir or underground mines. And again, using Cubit Python API, it was possible to automatically export model from Micromine into fidesis without any manual handwork or manual interfering. The model is automatically imported into fidesis. It is already filled in with the material properties like Young's modulus, Poisson ratio, and the analysis, 3D geomechanical analysis, is automatically done using fidesis solver. So the user automatically gets the result as the 3D stress and strain distribution of stresses inside the reservoir. And another example from this field, the field of oil and gas, is the integration with the RMS software of Roxar, which is a part of Emerson Group. And in this case, again, the 3D reservoir model with the block structure was automatically imported into a fidesis solver to perform 3D geomechanical analysis, like, for example, the computation of orientation of principal stresses, the vector field. And this information is very important for the geologists and geophysicists because it gives information of the secure locations for drilling borehole, for example, or secure locations for underground mines or optimization of hydrofracture as another example. One more thing I would like to give example on is the using Qubit Python API for our web-based solution SaaS called SymphoDesign. This is a totally different product, even it's not a product, it's a service, web-based service for designers, for people who are not experts in the simulation, there are not simulation analysts. Instead, there are designers who would like to try simulation at the early design stages to check where their design is robust or where it is satisfy some requirements dictated by the structural analysis. So this is completely pay-as-you-go, web-based service, architectured as a client-server approach, and at the backend, at the server, actually we're using again Qubit Python API to communicate between the front end, the web interface, and the comment generated by the user in the browser, and the backend, which is powered by Qubit Python API. So I welcome everybody to try us at symphodesign.com. And last but not least, one important thing with any software like this is, of course, training and education of engineers. And you could see here the photos from one of our training classes for young engineers, young designers. You could see even possibly the screenshots of the preprocessor at the computer classes, at the computer in the class. And once again, Qubit is very useful, and even not Qubit, but our collaboration with the Coreform here, because we obtained not only Qubit license, but also the training material, how to teach and how to train people, students to build the proper geometry, to build the proper mesh. And all of this information was very useful. Actually, the full training class of fidesis goes for 5 days, and the first 2 days completely dedicated to the analysis and education on meshing and geometry preparation. And here we're using actively training and educational material provided by the Coreform. So having said this, let me switch to the fidesis preprocessor, which I mentioned already several times, and give you a short overview how it looks like and what is the extended workflow additionally to what is available in the basic classical version of Qubit, what was extended and what was customized by us to provide the full simulation workflow, not only geometry and meshing. So we start in the traditional logic of the command panel, moving from left to right, top to bottom. And we start with the geometry. Let's say we would like to build some simple model like a brick. So we generate it using the standard command, and you see our actions in the GUI duplicated by the corresponding command in the command line. Next, we build the mesh. I'm skipping the overview of the first two parts because it's quite traditional, and of course you could see this in the Coreform webinars or Coreform tutorials, which is available on the Coreform website. So here is our geometry, the mesh, and the next, after we are done with mesh, the next step, which was introduced by us, by fidesis developers, is to specify material properties. And in order to do this, we created our own customized material management dialog window. And in this dialog, you could choose either some predefined material like steel, rubber, soil, or you could enter your own material name, like I did right now, and then choose the material model you would like to use for your particular simulation. We can start with something simple like linear hook materials, drag and drop Young modulus, and put some value to specify it parameter. Also, when we enter the value, we could also, let's say, add some dependency of the Young's modulus, let's say, on the temperature by saying that so temperature 0 is some value, temperature 1 is another value, like 10 and etc. So it can be specified like time dependency, coordinate dependency, temperature dependency, etc. If we need something additional, like let's say add plasticity parameters, we can also choose which plasticity model we would like to try, like Mises criterion or Drucker-Prager. What else? It can be thermal parameters if we are taking into account thermal plasticity or thermal elasticity material. And geomechanics, which I mentioned in my presentation. There are some additional parameters for the bio model, the classical model for poroelastic or poroelastoplastic materials, taking into account porosity, permeability, and fluid parameters, because this is actually the model of two-phase material of the poroskeleton filled with the fluid. So as you could see, there are quite considerable set of material parameters, and depending on the complexity of the model you consider it, you could always combine particular material set you're considering, like a Lego model, by drag and drop the parameters you are interested in. And then when you're done, you click apply. And as you could see, again, the custom comment were automatically generated in the command line. So these are additional comments, additional to the standard Qubit comments, and these additional model comments were prepared by fidesis to be fully compliant with the logic of Qubit, the logic that any action or in the GUI is duplicated by the corresponding command in the command line. And if we switch to the history tab, you could also see the history of all the operations here, including additional custom commands. So this is very useful not to interrupt the typical workflow of the Qubit. Next, we go to the blocks. I skipped the coordinate system tab because it's quite specific and not going to go into details today's webinar. We go to the block. We specify the block for our volume. There is only one volume. And what else we could make with our block? What additional, again, custom widget. This is the specification of the order of approximation, because fidesis, as I mentioned, is based on the spectral element method. And for the end user, it means that for the same mesh, like you see right now on the screen, we could actually do analysis with different accuracies. And the accuracy, the numerical precision is specified by the user just by a single click button choosing the order. So the higher the order, the better the accuracy. And the convergence with respect to the order value is actually exponential, thanks to the beautiful properties of spectral element method. So instead of refinement of mesh, and you know, I'm sure that sometimes rebuilding, refinement mesh is taking lots of time, we could just increase the order of approximation and get the accurate solution without touching mesh or other parameters of our model. And again, if you click apply, you see that the corresponding command is generated. What else? If let's say our model consists not only about solid, not only of solid elements, but also let's say we have beam or shell elements inside our model. As I mentioned, we could have a total element zoo for the model discretization. For example, if we have beam, we can specify beam properties. And in terms of beam properties, you see there is again quite a considerable choice of different cross sections which we can specify for our beam parameters. And if some, let's say, cross section is missing here, we can also put some custom section parameters with inertia. With an inertia parameters of the cross section. Okay, 1 second. And last but not least step of the workflow to specify the simulation model is to choose a boundary condition and analysis type. So for the boundary condition, as you could see, we extended the list of possible conditions, forces, pressures, additionally to what is available in the classical basic version of Qubit. For example, if we speak about the geomechanical models, one could specify pore pressure parameter, or one could assign the fluid flux. And once again, it's totally compliant with the classical logic of the qubit, because, for example, if we put, let's say, heat flux, or we put fluid flux, we could, as usual, we could choose what is the entity we would like to specify this boundary condition on. So we can specify it either on the geometrical entity like surface or curve, for example, or we can specify it on the edge, vertex, node, which is the mesh entity. Again, this is fully compliant with the traditional logic of the qubit Coreform. And moving forward to the last step of the analysis of the simulation workflow, we need to choose the type of the analysis of the calculation we would like to perform. As you could see, there is several options. We can do, for example, static analysis for 2D or 3D models. We can make it in a basic elastic for the elastic models, or if we would like to take into account some nonlinear effects like plastic or nonlinear geometry, we can also click on the check boxes, and in this case, the solver will take into account these nonlinear phenomena effects. Or for example, pore fluid transfer, if we would like to take into account two-phase BO model for the geomechanical analysis of the porous media. And for the advanced users, simulation experts, also there is additional options to specify some nonlinear parameters for the solver for the Newton iterations, like number of iteration, number of load substeps, etc. One interesting thing I would also draw your attention is specification number of steps, because the end user, especially in the underground mining, they introduce boundary condition, not instantaneously all of them, but step by step. Or let's say they originate stress concentrators or remove part of the materials, not in one step, but again in several stages. Or like in 3D printing, when we print layer after layer. So it's again multi-stage loading. And in order to simulate this process of multi-stage loading or sequential removal of the material, or let's say variation of material properties at different loading steps, there is a possibility to specify number of load step or number of calculation step in fidesis. And in order to do so, we can make the so-called active status of the block, and by default you see our block is active at the all steps, but for example we can specify that the block number 1 is active on the step number 3, and let's say block number 2 will be active on the only on the step number 1. And by doing so, we can switch on and switch off particular block at different loading step of our simulation process. So I think this is it for the general overview of the simulation workflow. Of course, there is much more functionality internal, and I invite everybody to try the trial version of fidesis and see yourself, and also have a look at the user guide of fidesis describing different options for specification of material properties, boundary condition, types of analysis. We overviewed static analysis, but as I said, there is also transient analysis for, let's say, full waveform simulation of the wave propagation using explicit scheme for the fast and time processes, or implicit for more slow transient processes. Model analysis, frequency analysis, like harmonic, for example, backlink analysis, analysis of effective properties of composite materials, etc. So general overview, and once again, welcome everybody to try fidesis yourself. And I think we have about 10 minutes left, so let me show you several industrial applications of fidesis for the geophysical and geomechanical industry. So let's start with example of drilling the borehole at the scale of the borehole, and later on we will go at a larger scale. So the first example concerns the 3D model, the problem of drilling the borehole and the problem of wellbore stability. Because when the oil companies perform drilling, sometimes the issue could happen, like sanding from the wellbore walls, or the total collapse of the wellbore, which could lead of course lots of resources. Just to give you an idea, sometimes drilling one single borehole could cost the company from millions of US dollars to thousands of millions of US dollars. And in order, of course, to prevent such a risky scenario and reduce the undesired outcome of it, of course, it's better first to build the 3D digital model of the borehole and perform different drilling scenarios in the digital model instead of going to the real field. So in order to do this, we implemented the plugin for several logging software, for example, TechLog, and this plugin allows to automatically reconstruct 3D model of the borehole, including the curvilinear shaped borehole, inclined borehole, or boreholes with a variable diameter measured by the special tool, which is measuring the diameter at different depths levels. And by implementing this plugin, we automatically reconstructed the 3D model in the fidesis preprocessor, again using Qubit Python API. And you could see that the borehole could be intersected by several layers with different material properties specified using the materials widget, which I just demonstrated in my live demo. And then we do analysis of stresses and deformation under the gravity. And this is on the right, you could see the full borehole starting as a vertical, and then it is deviated up to the horizontal part. And the horizontal part goes right internally the oil field layer of the reservoir. And you see that the maximum stresses, as it was expected, achieved in the horizontal part. And by analyzing this, the values of these stresses, one could make a conclusion whether there are behind some limit or still less. So we still have some safety factor. So it is keep and it is safe to drill this borehole. Yeah, or we can play with different geometries, for example, of the borehole, like, for example, the fishbone type borehole, like even the bunch of borehole when we have the major borehole and this secondary one, to maximize the covering of the oil field. And sometimes, again, drilling the secondary borehole could lead to the collapsing of the major wellbore, which is again there could be huge problem for the companies. That's why it's again better to simulate it in the as a 3D digital twin and play different scenarios of, let's say, the different mud cake fluid density, because depending on the mud cake fluid density, if it is not dense enough, we could come up with the so-called Luder's bands, which is actually the future fractures, shear fractures in the borehole wells. And these fractures could lead later on to the total collapse. First, they lead to the sanding, production of the sand from the borehole walls, which is again undesired process, and later on they could collapse to the origination of the larger fractures and total collapse of the borehole wells. And what I would like to show that, again, using spectral element method, you see we can achieve a much better resolution of these fractures rather than using standard finite element method, which is producing such a blurry and not a precise distribution of the plastic zones of plastic concentrations. And even we can you can see the animation, how this plastic zone and how this fracture start to propagate away from the borehole wells. And this is actually the spectral element mesh, which was used in order to simulate this process. So you see, initially we had some quite continuous distribution of plastic stresses, but later on, by decreasing the density of the mud fluid internally inside the borehole, we see that the pressure drop produce more and more concentration of plastic zones, and more we see how these plastic concentrators converge to the shear band fractures. So it's quite interesting nonlinear process. And another example is from mining industry, example of the underground excavation. And as you could see here, the real picture, the real photo from the real mine, and the comparison with the simulation in fidesis. And the feedback from our client was the simulation almost completely reproduced the deformations in the real tunnel, and the only comment was that the corrosion was not reproduced. Everything other was perfect. And later on, the client was capable to play with different types of the beams, different types of the tamponage, let's say how they are distributed, what are the steel parameters. And of course, playing and choosing the proper optimized variant is much safer and much faster in the digital model reconstructed in fidesis, rather than attempting different types of beams in the real tunnel, because it is, first of all, unsecure, and of course it takes more time and resources. And one more example, this is the 3D model, the complicated model of the true excavation, underground excavation, with the multi-level geometry, different tunnels, vertical wells, horizontal tunnels, and the core rock production itself. And as you could see, the geometry really complicated, three-dimensional with different material properties. But thanks to the powerful mesh generator available in Cubit, the client, which is totally not an expert in the mesh generation and the CAE software, and the client was capable to build adaptive mesh. You see the mesh size is adaptive to the geometry, and it was done completely automatic. And this is really a big advantage, and the robustness, the speed, the performance of Cubit is really important from this point of view. So I think this is it. And to conclude, once again, thank you for your attention. I invite everybody to our website. You see it on the website, on the slide. And after short registration, you can try fidesis yourself. The trial version is completely free for 30 days. And also at the website, you can find the user guide with step-by-step examples, with screenshot. And with this, thank you for your attention. This is my contacts, and I will be happy to answer your question. Thank you. Matt?
Yes, Anatoly, thank you so much for all the preparation you put into this and all of the great work that your team has done building on top of Coreform Cubit over the years. So let's kind of wrap up with this slide as well. And then we have a few questions to answer and maybe some more will come in. So to kind of summarize and restate what Anatoly was saying, so there's a couple next steps you can take after this webinar. If you are interested in learning more about using the Coreform Cubit API, then go ahead and just email us to request access to that. It's free with your license. And beginning in just a few weeks, the next version of Coreform Cubit, that will just come standard without any need to request additional access. But for now, just go ahead and email us and we can give you access to that. There's extensive documentation at coreform.com, and then we'll be excited to work together with you for your success. With fidesis, as Anatoly was mentioning, feel free to get a 30-day trial at their website, and you can reach out to Anatoly with any additional questions. So with that, we'll go ahead and answer some questions that have come in. There's a question from Rahul. Are there inbuilt Indian standard sections like channel, angle, or beam in the software? And Greg, maybe you could answer that on behalf of Coreform, and then Anatoly could answer that on behalf of fidesis.
Yeah, thanks, Matt. So I think, so part of the answer is that using the Coreform Cubit API, as well as, so all you've seen today is built in Qt. And there's open source free versions of like Qt Designer to help you build interfaces. And Anatoly can probably give more info on specifically how they built their API, or how they built their tools. But my hunch would be, at least in Coreform Cubit, you could certainly build your own workflow similar to what Anatoly showed. You could put in your Indian standard sections, including like the picture of like what the section geometry looks like, and then the field to be able to put values in. And then with the API, you can then access the results for the entered values and then put those into a script that then builds whatever you're looking for. So, Anatoly, I guess a question I would have for you then is, if someone had fidesis and they wanted to add their own standard sections or they wanted to maybe tweak, are they able to then tweak or add functionality to the fidesis CAE?
Yeah, thank you, Greg. Completely agree with your comment. And my addition is that actually there are two APIs provided by Cubit. One is available also for fidesis users. It is based on Python. It's Python API, and as I mentioned, as well as the Cubit, fidesis preprocessor and postprocessor completely compliant with this Cubit Python API. So any end user could write scripts in Python and run it inside fidesis and make automatization, customization, some scripting for fidesis and working with fidesis using API. One great example here is our SaaS for engineers and designers, Info Design, because the front end, as I mentioned, actually do nothing by just communicating with the backend using Python API. This is a way to communicate with the preprocessor. But of course, as you mentioned, there is also API based on C++, and Qt as a library is used by us as a developers, by fidesis developers. And using the Qt and C++ SDK provided by Coreform for the OEM licensors like fidesis, like us, it is possible to add additional GUI elements or some programming logic for the custom software. Using this C++ API, we develop our customization, our specific widgets necessary for fidesis simulation workflow. And briefly, I demonstrated them during my live demo. Going particularly to this question, there are standard sections, if I understand your question correctly, standard cross sections like L-shape, circle, ellipse, square, etc. Also, there is a custom cross section with the custom parameters which can be specified either manually using GUI or using scripting language. And I think we don't have something specific for particular country. To tell you the truth, we don't have even something specific for Russia. It's just a standard set of typical sections used by engineers and standard set of parameters for these sections. So anybody is welcome to try them or use custom parameters if one section is missing. And last option, of course, you're more than welcome to contact us directly, and we'll be happy to add your specific cross-section for your particular industry.
Great, thank you.
And Anatoly, would they reach out to get into contact with you directly if they have that request? Would they just email you directly, or should they email support?
No, they could email me directly, and then I will transfer to my colleague if it is necessary. Yeah.
Great.
Please write to my email.
Yeah. So there's a question from Rahul whether design codes are included in the software.
I don't think I understand completely the question. What you mean by design codes? Because I think it's more related to CAD rather than CAE, you know? Maybe you could comment, maybe you can help me, Matt.
Yeah, maybe Rahul could clarify that. I wonder if he's referring to the CAD integrations that you've done. And of course, those CAD softwares are sold separately. So he says like ASME codes.
I can comment here that, as I mentioned, fidesis is a member of NAFEMS, so we can say that somehow we have our internal NAFEMS code inside fidesis because all our solvers are verified accordingly to NAFEMS standard benchmarks.
And maybe something that would help a little bit. So, right, so you showed some of the, because I think I understand where Rahul's going. You showed like some of the pre-built, here's how you can build some sections. So certainly, right, we could add different sections that maybe comply with a different standard or a different ASME code definition. But Cubit is not necessarily what you would consider a constructor or a builder of CAD geometry. It is not going to replace a tool like SolidWorks or Creo for building geometry from scratch. It's much more common that it's used as a consumer, where if you've got a specific geometry that you need for like an ASME standard test, typically you build those in a CAD tool and then you import those into Cubit for meshing. That's typically the workflow. We do have on our roadmap to improve Cubit in that area, but that's certainly not a standard workflow yet in Cubit.
Greg, agree and not agree as well, because I should say that some of our clients, and there are quite few of them, that are using Cubit also as a geometrical builder, especially in geophysical and geomechanical industries. I'm surprised myself how complicated geometry some of our users are building without going into any additional software, just using Cubit geometrical preprocessor.
Right.
So it's quite powerful.
Yeah, that's a very good point. I guess the point that, or the comment that I'm making is that it's not a parametric modeler where you're defining, you're like defining things as being tangent or distances between things and then solving some constrained system. But with Python scripting, you can absolutely build, if you have a very specific code that you want, you can build Python scripts that accept inputs, and then you can integrate those into the GUI for rapid access.
Right.
And
You
I've
could
seen
introduce
a
your
lot of
own.
people do that.
You could
Yes.
introduce your own variables, loops, condition statements, and using this like a programming language, you could use ApriPro to build even complicated scenarios of
Sure.
geometry.
And if you, Rahul, you might be interested then to attend the webinar later on Python scripting. And I would encourage you, if you wanted to send Coreform an email, maybe with one of your either ASME codes or Indian standards, and I'll make sure to include showing how you would script the construction of that geometry and then put that into the GUI for Qubit. So if you'd be willing to provide that, we'd be happy to add that in our demonstration.
Great. Okay, well, thank you everyone for attending the webinar. Thanks again, Anatoly, for your great preparation, your great content, and look forward to seeing all of you at an upcoming webinar. Hope you all have a great day.
Thank you, Matt. Thank you for organizing, and thank you everybody for attending and your questions. Hope to stay in touch with you.
Great, thanks, Anatoly. Bye.
Yeah, bye.